So, last time we solved some problems in relativistic dynamics. Today again the agenda is to solve more problems and some specific methods you will learn from these problems today. So, our first problem is a particle of rest mass m1 moves with a speed c sin theta in positive x direction and another particle of rest mass m2 moves with a speed c cos theta in negative x direction. If the total linear momentum of the system is 0, find the ratio m2 by m1. So, we have a particle of rest mass m1 which is going in this direction and the speed is c sin theta for some theta, and you have another particle of rest mass m2 which is going with some other speed which is c cos theta, and the total linear momentum is 0. So, in non-relativistic dynamics, if I say that total linear momentum is 0, it is very simple, m1 times this should be equal to m2 times this, and therefore, m2 by m1 should be sin theta by cos theta, which is tan theta. But if relativistic equations are to be used, then you have to write the linear momentum, magnitude of linear momentum of this particle p1, that will be m1 times c sin theta and then divided by square root of 1 minus v by c. So, sin theta square, and p2, this is cos theta, and so let me write. So, this is m1 times c times sin theta and then divided by cos theta, and p2 similarly, if you write the magnitude of this linear momentum of the second particle, it is mass times velocity divided by that square root factor. So, m2 into c cos theta and divided by square root 1 minus v by c whole square, that is cos theta square. So, it is m2 and then c cos theta by sin theta. So, if total linear momentum is 0, these two should have the same magnitude, and therefore, this should be equal to this here. So, m1 sin theta by cos theta should be equal to m2 cos theta by sin theta, and hence m1 by m2 will be, or m2 by m1 we need. So, m2 by m1 will be sin square theta by cos square theta, that is tan square theta. Right. So, this will make the total linear momentum 0. So, let us go for the second question. So, here is the second question. It says that a particle of rest mass m0 moves at a speed v towards a stationary identical particle. So, you have a particle of rest mass m0 which moves with a speed v towards a stationary identical particle. So, the rest masses are same, but it is stationary, it is at rest. Find the velocity of the frame in which the total linear momentum is 0. So, this is our lap frame, and in this lap frame you have total linear momentum. Linear momentum of this particle is 0, but this will have linear momentum. So, you have to find the frame in which the total linear momentum of the two particles is 0. So, if that frame is moving with some velocity, let us say capital V, this is the frame in which the total linear momentum is 0, then in this frame what is the velocity of this particle and what is the velocity of this particle? Velocity of the second particle is very simple. In this frame from S prime, if I see, then this particle, second particle m0 will move in this direction with this velocity capital V. and this particle, first particle, that will move some velocity, and that velocity is given by, that velocity will be given by velocity transformation equation v minus capital V divided by 1 minus v capital V by c square. That is the velocity of this particle in this frame. And if the total linear momentum is 0, then the magnitude of this linear momentum should be equal to magnitude of this linear momentum. And since the rest masses are same and linear momentum is given by, let us say this particle, it is m naught times capital V divided by square root of 1 minus v square by c square. And here if this is u, then this will be m naught u divided by square root of 1 minus u square by c square. So, if these two are to be equal, this u should be equal to this v. If you have the same rest mass particles and then they are moving towards each other and the magnitude of linear momentum should be 0, total linear momentum should be 0, then their speeds must be equal and opposite. So, this u is same as this v. So, our equation is this v small v minus capital V divided by 1 minus a small v capital V by c square, that is this quantity, and this should be equal to capital V. So, this should be equal to capital V. So, we can obtain capital V from here, but it is a quadratic equation, as you can see. It is v minus a small v capital V square by c square is equal to v and minus capital V. So, let us take everything to the right hand side. So, you have this becomes positive, v capital V square by c square, that goes here. Then you have this v coming here. So, it will be minus 2v and this is plus small v, this is equal to 0, or v capital V square minus 2c square into v and plus vc square is equal to 0. So, I can use my class 10th, class 9th algebra. This v I have to find. So, v is equal to, capital V is equal to minus b, that is 2c square, and plus and minus the square root of b square minus 4ac. B square is 4 times c4 and minus 4 times a into c. A is small v and c is vc square. So, it is v square c square and divided by 2a. So, it is 2v. So, first you can cancel this 2 from everywhere and this will be c square and then plus and minus square root of c4 and v square c square. So, c4 here and minus v square and c square here and divided by v. So, if you take a c square common here or c4 common here, so square root of c4 you take here. So, this is c square. So, this is equal to c square and then plus and minus c square here and then square root of 1 minus v square by c square, and this whole thing divided by v. So, this is equal to c square by v and then 1 plus minus square root 1 minus v square by c square. Okay. C square take common, c square by v is here, v is in the denominator. So, 1 plus minus square root of 1 minus v square by c square. Now, this is capital V. This is the velocity with which this s prime has to move. If the total linear momentum is 0, and this quantity c square v is already greater than c, because small v is the speed of the first particle, which cannot exceed c anyway. It has to be smaller than c. So, this quantity is already greater than c, and this capital V also cannot be greater than c, and therefore, this plus sign is ruled out, and hence the frame velocity is c square by v and 1 minus a square root 1 minus v square by c square. So, a frame which moves with respect to lab at this velocity, in that frame the total linear momentum will be 0. If it was non-relativistic, the answer was very simple, it is small v by 2. Then here this becomes v by 2 and this becomes v by 2 in opposite direction, and linear momentum is 0. But now it is this, we call it zero momentum frame. Zero momentum frame. I will often use this, so let me abbreviate ZMFF, ZMF, zero momentum frame. In this frame the total momentum is 0. In non-relativistic mechanics we used to call it center of mass frame. In the frame of center of mass, the total linear momentum is 0. So, zero momentum frame same as the center of mass frame. Whether you want to still have that word center of mass frame or not, I think that is your choice, but I will call it zero momentum frame. So, this is the question. Two protons move towards each other with same speed v and collide. So, you have two protons, say rest mass m naught, and they move towards each other with same speed v and collide. As a result, a new proton and an antiproton is created. So, because of this collision, this is before collision, and after collision you have 4 particles now. You have a particle, this particle are there, the protons are there, and you have another proton, new proton, and some antiproton. This 4 particles are there, they may be moving in some directions. So, as a result, a new proton and an antiproton is created. Find the minimum value of V for this to happen. So, what we are doing? We are colliding two protons towards, moving towards each other, and then because of this collision, kinetic energy is being used to create new particles. So, the original two protons are here and one more proton is created, and corresponding antiproton which has the same rest mass is also created. Now, to create these two new particles, you need some minimum value of this V, and that minimum value has to be obtained. It is a very regular experiments, regular kind of experiment. The two proton beams are colliding each other, new particles are being created and being studied in our LHC, and before that many more accelerators have done these kind of reactions. So, what is the minimum value of this V? So, the linear momentum must be conserved, this is important. The linear momentum must be conserved, and here the linear momentum is 0. The two particles are identical rest masses m naught, m naught, and then the speeds are also identical. So, the total linear momentum is 0, they are in opposite direction. Here also the total linear momentum should be 0, and therefore, our arrows must be different. Some of the arrows should point opposite direction, so that the total linear momentum is 0. So, the kinetic energy here and kinetic energy here, the difference is creating this new rest mass. and therefore, if you want minimum value of this V, then the kinetic energy here should be minimum, should be 0. So, that this entire kinetic energy is converted into rest mass, and that is possible. All the 4 particles at rest. So, this configuration is just some PPP and P bar all at rest. This is possible because it follows principle of linear momentum conservation. The linear momentum is 0, here also linear momentum is 0. So, this is possible, and if this is possible, then this will correspond to the minimum value of V there, because we are not creating any kinetic energy, no more kinetic energy here. The energy which is available to create this new mass is this kinetic energy and minus this kinetic energy. So, in order to reduce that, I should reduce this, and we can reduce it up to 0. So, this should be 0, and then for that case the kinetic energy here, how much is the kinetic energy here for this particle? Let us say for this particle the kinetic energy is m naught c square 1 by square root 1 minus v square by c square and minus 1. Right? You remember, this was the expression for kinetic energy for this particle, and similarly for this particle, and therefore the total kinetic energy is this. And the total energy is m naught c square plus m naught c square and plus this kinetic energy. And here 2 of the particles will have m naught c square, m naught c square, which will be same as this, and the new rest mass that is created, that should come from this kinetic energy, and therefore this should be equal to 2 m naught c square 1 by square root 1 minus v square by c square minus 1, that should be equal to 2 m naught c square. This is the new rest mass energy that has been created due to collision. The 2 particles, one extra proton and one antiproton, that rest mass energy is here, and that is coming from this kinetic energy. So, now you can work out, this is 1 by square root 1 minus v square by c square is equal to 2. So, square root of 1 minus v square by c square is 1 by 2. So, 1 minus v square by c square is 1 by 4, v square by c square is 3 by 4, and therefore, v should be equal to square root 3 by 2 into c. That is the minimum speed each of these 2 protons must have, so that this creation of proton and antiproton can take place. Now, we will just modify this question, we will go for another question having the similar framework, but now the 2 particles in the lap frame, the 2 particles will not be going towards each other, one proton will be hitting another proton at rest. So, here is the question, a proton moves at speed v towards another proton at rest. So, now I have a proton which is moving at speed v towards another proton, and this proton is at rest, and rest is same. As a result, a new proton and an antiproton is created. Find the minimum value of v for this to happen. So, rest is the same. So, what we can do is, we can go to the 0 momentum frame and then solve the problem and come back to this frame. This is our lap frame. So, if we can go to 0 momentum frame, and in this frame this particle will move with some velocity u, and this particle will move with the same velocity u, both of them are protons. And you know what is this u? This u is, we had just done c square by v, and then 1 minus square root of 1 minus v square by c square, that we had done. So, if you go to this 0 momentum frame which moves with respect to lab at this velocity u, so that in this frame the second particle goes in negative direction with speed u, and the first particle also goes with the same speed, then the linear momentum is 0. And then if I demand that after the collision, so in 0 momentum frame, after the collision you have P, you have P, you have P, and you have P bar, all are at rest, then you will get the minimum value of this u, and then you can find the minimum value of small v. But that will be a tedious algebra, but there is a beautiful way of doing it, absolutely fantastic. So, this is the lab frame, and let me do it again. So, in the lab frame, this is before the collision. In the lab frame, what will be after the collision? You will have 4 particles, and 4 particles must move because there is a momentum, and therefore the 4 particles must move, and hence you have the 4 particles P, 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 P. You should have a forward momentum. So, I do not know which way, but maybe something like this, maybe something like this. The particles are moving, 2 protons original, 1 new proton and an antiproton, and they are all moving, so that the linear momentum is same as this linear momentum. And this is because before the collision, after the collision, the linear momentum does not change, the energy, total energy does not change, that energy momentum conservation principle. So, before the collision you have some momentum, same momentum you will have here. Before collision you have some total energy, the same total energy you should be here. So, this is lab frame once again after the collision. We are still looking for minimum value of V, but we cannot make all of them to be at rest because I have to conserve linear momentum. So, what combination of velocities will ensure that this V is minimum, that we have to obtain. Now, in 0 momentum frame, this is the original situation, and after the collision what we demand is that they should be at rest. So, this is after the collision actually, let me write it here itself, this is after the collision. And this is before the collision. So, in 0 momentum frame, before the collision both are going with the same speed, and then after the collision all of them are at rest, corresponding to the minimum value of V. Now, think of this quantity, total energy of the 2 particles is E, and total linear momentum is P. And think of this quantity E square minus P square C square. If I go from here to here, from the lap frame before the collision, again in the lap frame after the collision, E does not change, P does not change because of law of conservation of energy momentum, and therefore, this E square minus P square here, P square C square, and this E square minus P square C square here must be same. These two must be same, because before the collision, after the collision, total energy here, total energy here, total momentum here, total momentum here, they do not change, and therefore, this quantity will remain the same. Now, after the collision, in the lab frame this quantity, and after the collision in this 0 momentum frame, here also calculate what is E square minus P square C square. So, the situation is same after the collision. I am looking at that from the lap frame, and the same situation I am looking from the 0 momentum frame. So, I am going from one inertial frame to the other inertial frame. I am not looking at the time development. The same situation I am looking from lap frame, the same situation I am looking from the ZMF, and this quantity is Lorentz invariant. When you do all kinds of Lorentz transformations, E will be different here and E will be different here, P will be different here and P will be different here, but E square minus P square C square is same, and therefore all these three are same. This one and this one, all values of E square minus P square C square is same. Okay, so let us calculate this from here before the collision in the lap frame. So, what is E? Now you have two particles. So, you have E1 plus E2 square and minus P. P is again combination of these two, P1 plus P2. Here P2 is 0, this is square C square, that is the quantity. So, this will be E1 square plus E2 square and plus 2 E1 E2, and then minus this P2 is 0. So, P1 square C square. So, how this E1 square and minus P1 square C square, okay, is one particle now, one proton only. E1 square minus P1 square C square must be m naught square C4. So, these two together makes it m naught C square, m naught square C4, this minus this. E2 square again must be same, second particle is anyway at rest. So, its total energy is same as rest mass energy m naught C square, and therefore, its square is 2 m naught square C4. If P2 is not 0, then you will have a P square minus P2 square C square, that together with it, that E2 square will again make m naught square C4. Then plus 2 times E1 E2, 2 times E1 E2. Now you have to write E1. So, I am looking here lap frame before the collision, E1 here. So, it is m naught C square divided by square root 1 minus V square by C square. Remember, total energy m naught C square times gamma. So, for this particle m naught C square times gamma is this, and then into E2, and E2 is total energy of this particle, which is just m naught C square. So, this is the value of E square minus P square C square before the collision seen from the lap frame. And if I look at this here after the collision in the 0 momentum frame, they are all at rest. So, the total energy is 4 times m naught C square, and hence the total energy square minus P square C square, this is 0, this P is 0. So, it is just E square, and hence this whole quantity is 16 times m naught square C4, right. I am writing this quantity, P is 0, none of these 4 particles is moving, and therefore, this P is 0, and hence E is simply 4 times m naught C square, and E square is 16 times m naught C square. And now you can do the algebra very simply. You have m naught C square, m naught square C4, you can cancel it first. Then you have 2 here which can go on that side, making it 14. Then you have 2 here making that 7, and therefore, what you are left with 1 divided by square root 1 minus V square by C square is equal to 7. right? This is 16 and minus 2 is 14 and divided by 2 is 7. So 1 by square root 1 minus v square by c square is 7, and that tells me square root of 1 minus v square by c square is 1 by 7. So 1 minus v square by c square is 1 by 49. So v square by c square is 48 by 49, and therefore v is equal to square root of this, which will be 2 times 4, this is 16, so 4 times, let us say 4 times the square root of 3 and divided by 7 times c. This should be the minimum velocity. 4 times root 3 by 7 times c, this should be the minimum velocity, minimum speed of this particle, which can hit this stationary particle and create a proton and an antiproton. So this is a very powerful technique to solve such kind of problem, that Lorentz invariant and conservation, both you can utilize. So before the collision you can work in one frame, after the collision you can work in some other frame, and still you can say that E square minus P square C square is same, or all Lorentz invariants which are also conserved, you can use this kind of technique.